morning, I'm Sebastiano Dissegna, and I've been working on the development and implementation of a novelty approach to check whether a formula in pure-path linear temporal logic is realizable or not. The realizability problem is the first part of the problem known as synthesis. Synthesis can be viewed as a two-player game between an environment and an agent. We start by a specification, which is a temporal formula expressed over two sets of variables. An input one represented by the set X and the output one represented by the set Y. The input one is controlled by the environment, while the output one is controlled by the agent. In this game, the environment will try to violate the specification, while the agent will try to satisfy it. The problem consists in building a system such that for every possible execution of it, the specification is never violated. So, for every possible move of the environment, the agent can respond to maintain the formula satisfied. The realizability problem consists in checking whether such strategy exists. We choose to work on specification written in pure-path linear temporal logic on finite traces because no one did it before, and also because most AI applications work on finite traces and some properties are easier to express using path operators. The syntax of a pure-path LTL formula is the following. Including the standard Boolean logic operators, we also have 4 path operators. These formulas are evaluated over a finite sequence of states, which are called histories, and for a formula to hold, it must hold in the last state of a trace, because we look at them backwards. Our approach is the following. We first convert our specification into its previous normal form, which rewrites the formula into present and past components. Then we build the DFA automaton, which represents the two-player game, and then we run the check realizability algorithm on it. This algorithm works in the following way. We take as input the automaton and the two sets of variables. Win will represent the set of winning states, and it is initialized with the set of final states where the formula is satisfied. Realizable is a Boolean flag, which is initialized to false. We will keep iterating until either we reach the fixed point on the set of winning states, or we reach the set of initial states. In the while loop, we first update the old set of winning states with the current one, and then we update the current one by adding the set of states obtained by computing the strong preimage. And we must accumulate the set of previous states in order to guarantee the fixed point. Then, if the set of initial state is reached, it means that we found a strategy and the formula is realizable, so we can exit the loop. Here we have the formula definition of previous normal form and the one of the symbolic DFA and the one of the strong preimage function. We implemented algorithm within the NUSMV symbolic model checker, leveraging on a BDD, which are binary decision diagrams. And we also implemented a tool which we called Baseline, which is a C++ naive BDD implementation. We generated several datasets of random pure-path LTL formulas of varying temporal depth and number of propositional atoms, along with their equivalent LTLF counterparts where possible. We then compare our tools with the state-of-the-art LTLF synthesis tools Nike and SyftMax, and we can safely say that our tool is comparable with state-of-the-art LTLF synthesis tools of more formulas, and compared to Baseline, it also scales better when increasing the temporal depth and the number of atoms of formulas. In the future, we can improve the approach in several ways, such as optimization of the strong preimage computation to leverage optimization typical of model checking, for example, like conjunctive partitioning. Then we can extend the experimental analysis, and we can implement the extraction of the automaton to represent the synthesized strategy. And that concludes my presentation. Thank you for your attention.